So, we skim through this, ionic bonds. Then there's something called a covalent bond. Covalent bond is one atom is not strong enough to remove an electron from another atom. So what do they have to do to get to, what can they do? They can't take away electrons or give away electrons. They have to share the electrons. And that's called a covalent bond. You have a bond based on sharing of electrons, covalent bond. And how many electrons are needed to form a bond? Covalent bond, 2 electrons. And this slide here stating that why do atoms come together to form a bond? Because to lower its energy. If it doesn't lower its energy, why would they come together? They just stay apart. So this little graph here shows when an atom comes closer and closer together, it lowers its energy and they share electrons. If they don't lower its energy, then why would these things come together? They wouldn't. They would just stay separate. So this is a little diagram of energy and covalent bonding. And again, like chlorine here, sharing of electrons. Right? That's why chlorine doesn't exist by itself in nature. Oops. An atom like Cl doesn't exist in nature because what happens, there's always another Cl next to it. We're not talking about one atom, we're talking about Avogadro number of atoms. So what happens is this Cl is not stable, so what it's going to do, it's going to share electrons with another chlorine, and in nature we see Cl2, not Cl3 or Cl4, Cl2. And how can we predict why it's Cl2, not Cl3 or Cl4? Octet rule, right? They want to share electrons to get to 8 electrons. Right? So valence electrons, octet rule. This is how we draw the Lewis structure. But this is a rule, right? Rules are meant to be broken. So there's a lot of exceptions to this rule. When you share 2 electrons, you have a single bond. Share 4 electrons, double bond. Share 3 electrons, triple bond, or 6 electrons, triple bond. When we talk about electrons, there's electrons that are involved in bonding, and there's electrons involved in non-bonding. So non-bonding electrons are sometimes called non-bonding or lone pair. Right, so examples of drawing Lewis structures. When we share electrons, electrons can be shared. It doesn't have to be 1 electron from one atom and 1 electron from another atom. It could be 2 electrons from one compound and no electron from another compound, and they could share electrons. When you share electrons, you don't have to share electrons equally. You can share it unequally, right? So here's an example in which you have 2 electrons being shared, but more electrons are on this side of the atom than the other side of the atom. So this is just a review because we talked about this before. Electronegativity. Some atoms want electrons more than others. So depending on how much they want the electrons, you can have a different type. You could have covalent bond, basically means non-polar. Polar covalent means sharing of electrons, but sharing unequally. And ionic means they're taking an electron completely away. Electron transfer, no sharing. Okay. And depending on how to determine it's polar or non-polar, covalent, you look at the electronegativities, subtract the 2 numbers, and the 2 numbers come in this range. The difference comes in this range, is covalent, this range, polar covalent, larger than that, ionic, right? And shape impacts polarity, right? If it's very symmetrical, it's going to be non-polar. Practice drawing Lewis structures. There's some compounds that are both polar and non-polar. I mean, some compounds that have covalent bonds and ionic bonds. So this is an example of that. Resonance structure, formal charge. And why do we need formal charge? Formal charge is a way to calculate the charge on all these atoms. And here's an example. Let's see, we want to draw the Lewis structure of H2SO4.
I had a question on formal charge.
Okay.
On the previous slide, For the formal charge calculation, the first one, are we using the non-bonding electron in half for the first one, but the valence electron for the S?
This
Because I
6
see a
here,
4. Yeah,
that 6 here means what column am I in? Column 6, right?
right?
Total valence electrons. This 4 represents, so you look at this oxygen here is this oxygen right there.
Yes.
How many electrons are involved in non-bonding?
Oh, that's right. Okay, 4.
4.
Okay.
Yeah. So something like this, you have to draw the Lewis structure.
Okay, and then we draw the Lewis structure, or it's like sometimes you give it, or sometimes we draw it.
Oh, you're going to have to know how to draw it.
Okay, and then we look at for the non-bonding, it's the ones that do not connect directly to the center.
Yes.
Got
You
it.
got 4 non-bonding. And how many bonding? 4.
2.
And then 1/2 times 4. That's the formula. So then you get 0, +1, and -1 for all these atoms.
Got it.
Perfect. Thanks for that question. If you had that question, other people had the same question. So
Cool.
thanks for speaking up. Then, so we got these formal charges. Figure out what are the charge of these atoms in the compound. All right. Now here's another compound, H2SO4. When we draw the Lewis structure of this, we draw something like this. He goes, okay, I got 8 bit. Everything has the octet rule if I drew it this way. But in nature, this is not what we have. In nature, we have this. And how can this be? The S doesn't have 8 electrons. The S has 1, 2, 3, 4, 5, 6. It has 12 electrons around that S. That doesn't obey the octet rule. But in real life, this is the answer. This is what we see in nature. And go, why is that so? So now we have to tweak the octet rule. Now we have to tweak it. So when we tweak it, we go, why isn't the octet rule working here? So we look at the charges of each single atom. So the charge on this oxygen, -1, sulfur -2, this one -1 when we do the formal charges. And when we do the formal charges on this one, 0, 0, 0. Which one is going to have lower energy? Ones that has a lot of charge, or the ones that have all 0 charges? Which one's going to have lower energy?
0 charge.
Yep. So that's how we kind of justify that. Okay, the reason why the octet rule is not working is because this one's going to have lower energy due to the formal charge. Yep. And the overall charge is 0. Both of these are 0 charge. If you add up all the charges, they're all 0. But the one on top has this -1, +1, +2, -1. There's a lot of internal, what would you call a lot of internal friction in there, right? So what do atoms want to do? Do they want to have high energy or they want to have low energy? Do you guys want to watch TV? Right? Exactly. So these atoms, what are they made out of? Protons, electrons, neutrons. Can they talk to each other? No. So what's the language of chemistry? Energy. So how do things be low energy? So the octet rule doesn't work here, but how do we justify or kind of tweak it to show that, tweak the octet rule is by formal charges. So we say, oh, we have lower formal charges. That means we have lower energy. That's why it's called the octet rule. There's exceptions to that rule. And chapter 9 or chapter 8, next chapter, we're going to be speaking to that. So again, this is just a review of this chapter. So we're just going through it really quickly because we already talked about this. So when you could draw 2 Lewis structures, so both these 2 structures are both Lewis structures, then you have to make a decision which Lewis structure is the correct one. When you could draw two Lewis structures, then you have to go calculate the formal charges. And we have this slide over here, calculate the formal charges. And the one that has the lowest number of formal charges is going to be the correct structure.
So here we only calculate the charges on things that are directly connected. So we're not going to do hydrogen, or we also calculate formal charge for hydrogen. Or no, because it doesn't have any extra electrons. Or
You're going to do the formal charges for everything.
Okay.
But just in this situation, the formal charges, what I just circled, the H and the O, they're the same. for both compounds. So in this
Correct.
slide, we're just showing the differences. These formal charges and these. But the other ones, you're going to calculate those too, but they have the same formal charges.
Oh, okay.
They have the same non-bonding electrons, same number of bonds, so they're going to be identical.
So when we recognize identical structures, we're not comparing that because they're already the same. So compare obviously what's different in the structure.
Yes.
Got it.
So you could go ahead and calculate the formal charge in each one, but just the shortcut is, oh, they're both the same,
Right.
so there's no difference.
Okay.
All right, great question, great question. So this is what we said in words, right? We want to have a structure with fewer formal charges. Smaller formal charges is better structure. And rarely do we get to this case, but basically the structure that has a negative charge are going to be the nonmetals, or the most electronegative atoms. All right, and then we talked about this one last time, resonance structure. So we could draw a compound like this. We're going to have 3 resonance structures. We could draw 3 Lewis structures, and all 3 structures are identical. And then we call that resonance, right? Let's go on. Then exceptions to the octet rule. Here's a compound, PF5. This is a compound exists in real life, but look at this one, P. Okay. How many electrons around P? Bonding electrons, not 8, but 1, 2, 3, 4, 5. So that's 10 electrons, right? So that goes against the octet rule. So there are exceptions to the octet rule. Then again, these bonds have energy. When you break a bond, they're going to have energy. And again, this octet rule, we predict things that have a double bond, triple bond, single bond, and so forth, right? What do you think is easier to break, a single bond or a triple bond?
Single.
Yep, single bond. Then we look at the amount of energy to break a single bond, 347. The amount of energy to break a triple bond, 837, a lot more energy, right? So this idea of single bond, triple bond, octet rule, we see that experimentally, right? Because we predict the triple bond is going to be stronger, it takes more energy to break. Single bond is weaker, easier to break, right? So these lines, these atoms, they don't have lines connected to them in real life. These lines, the sharing of electrons, that's just our model to try to understand how bonding works. Now, what experimental data do we have to show that there's such a thing as a double, single, and triple bond? The amount of energy to break these bonds, right, is consistent with our logic of stronger bonds. Right? And again, we already talked about this. I'm just skimming through it all really quickly. In this slide here.
One question.
Yep.
The equation, is it delta H equals the sum of D bonds minus the sum of D bonds formed?
All right, that's a great question. So you want to say, is this number here is a negative number? Is that what you're asking for?
Yes.
Basically. Okay. So what we're going to say is, let's look at this one here. All right, here's a good slide to talk about. Okay, let's look at this slide. So let's look at this simple right here. Carbon bond. How much energy does it take to break this carbon-carbon bond on the slide? What does it say?
345.
345. What happens if I put in 344 units of energy? Can I break that bond?
No.
What was that?
No.
No. So this bond has some energy, right? So to break that bond, I need 345 units of energy. Why do I need 345 units of energy to break that bond? Because why? This carbon and this carbon, they're connected with some energy, with some force. What energy is it holding it together? How much energy is holding that bond together? 345 units of energy. So if I want to break this bond, how much energy I have to put in? Plus 345. How about if I have a carbon-carbon over here? They're not bonded to each other. But then they're going to get close together. Then they're going to form a bond. What happens? What happened to that energy? How much energy does it take to form this bond, to make a bond? It also
345.
takes what?
345.
But negative or minus?
Negative. Negative. Why negative?
Because formed bonds lose energy. I mean the
Yeah.
opposite. Wait, I get confused because it's opposite. 345. Formed bonds lose energy. Yeah.
Why would two atoms, they're happy by themselves, why would they want to come together to form a bond? To go lower in energy or to go higher in energy?
Go lower.
Go lower, right? When you watch TV, you spend 2 hours standing up watching TV, or you sit down. You sit down because you could be lower energy. So atoms, same thing, they're happy by themselves, but why would they want to come and form a bond, connect together to lower its energy? That's why it's a negative sign. And how much are we going to lower the energy by? Well, it takes 345 units to break that bond. That means it's going to take 345 units to make that bond, but it's going to be a negative sign.
So that's something that would be specified in like a theoretical question, like these two form a bond or these two break a bond, or we recognize that from a Lewis structure?
No, we're going to recognize this from, look at this chemical, we'll go through this example. We went through that on the last video.
Uh-huh.
So let's go through this one and then let's see if you have the same question.
Okay.
Here's this reactants, and these are the products. When I have a reactant, what do I have to do? I have to break some bonds, right? And a product, I'm going to have to make some new bonds. If I don't break bonds or if I don't make any bonds, nothing happens. No reaction.
Right.
So look at my product here. Oh, I got a carbon-carbon single bond. Here I got a carbon-carbon double bond. What do I have to do? I have to break that bond.
Oh, okay.
Look at this group here. OH. I got an OH group over here, but I actually got one more OH. What happened to that other OH? I have to break that bond. You guys follow me so far?
Mostly.
So, because I have to break these bonds, and then I have to, after, it's like having you have like a Lego pieces, making like a car. You have like 20 Lego pieces to make a car, but now you want to get those Lego pieces. I want to get the same Lego pieces and make a boat. What do I have to do to those Lego pieces on the car? I have to break it into individual pieces, then put it back together. So this is what we're doing on the reactant side. We're breaking apart these compounds, and then we're going to put it back differently to make the product. So when we break it, if I break this carbon double bond, how much energy do I need to break that carbon double bond?
Positive 611.
Positive 611. And what we mentioned last time, there's people who calculated or they've got all these numbers experimentally. So we have a table for that. Then what else do we have to break over here? OH, 464. There we go. So now the energy we need to break the bond is 611 plus 464. Now on the right side, we have to make new bonds. What bonds are we going to be making? I got to make a carbon-carbon single bond. Where's the carbon-carbon single bond? Right there. But now I'm making a bond. So what's my energy going to be? Positive or negative?
Negative.
Negative, because we're making bonds. Why would bonds come together if, right? Because they want to have a lower energy. Then what else are we making? Here we have a carbon and two hydrogens. Now we got a carbon to 3 hydrogens. So we're making one more CH bond. Where's the CH on this table? Oh, right here, 411. Now we're going to have minus 415. What else are we making on the right side that's new?
Carbon, oxygen.
Carbon, oxygen. Where's this table on carbon, oxygen? Right over here. And these are all negative numbers, right?
Yes.
So now what we're going to do, what is delta H of this whole reaction? We're just going to get this number and these numbers and add them together. And we do that in the bottom here. 611, 464 minus 345 minus 415 minus 350. And what number do we get? Delta H is minus 35. Oops.
Professor, so
Yes.
formed bonds are always negative because it's exothermic?
Yes. Not because it's exothermic. So remember what we said, why would we form a bond? Because we want to have a lower energy. And we have a lower energy, it's going to have a negative number.
Okay.
And then when you have a negative number, it's going to release that energy. And yes, that is exothermic.
Okay, because what threw me off was the delta H formula that said delta H products minus delta H reactants, but the products, like it's inside the product is positive, it's plus. Does that make sense? Yeah.
Yeah, that makes sense. So when we remember we mentioned products minus reactants, right?
Uh-huh.
So if you use this formula, then you just keep all these numbers here as positive. You don't put a negative sign because the negatives are already built into there.
Okay. Okay, that makes sense.
So that's, I think you're just following the, so if you use this formula, then you just, all these numbers will always be positive, but then
Uh-huh.
you have a
The negative
sign.
makes it negative. Okay.
It's going to make all these numbers negative.
So is it, while we're learning, a little easier to use the sum of delta H bonds broken plus bonds formed?
Yes.
That's a little easier for this because, yeah, that was confusing me too. So if we use bonds broken and bonds formed, it tells us that the broken ones are positive and the formed bonds are negative.
Yep, that's why I put this equation on this one here. Yes.
Oh, okay, yeah.
Yes. So if you put a minus sign, then sometimes you don't know what's going on, but what's really going on is bonds are being made, bonds are being formed, and when you make a bond, minus number, right? We want to be, it's going to go lower energy. When you break a
Right.
bond, you have to put energy in.
And then if there is a reaction, like on the other side of stuff is changing, that means there is a reaction. That means things had to be broken.
Yeah.
I don't know if that logic makes sense.
Yes. Yeah. There's a reaction. If it involves molecules, things are being broken.
Right.
They're being put back together in a different way. Yep. And then we get this number, minus 35 kilojoules. Now this is just all theory, right? We just got a table, get these numbers together. How do we know if that number is true or not? Again, what is the answer? What is the answer in the back of the book we do in real life? We do a what?
An experiment.
Experiment. And what do? We get these same compounds. I put them into my calometer, do this reaction, and I could determine what is the delta H of this reaction. And you know what the delta H is? Experimentally? That number. So we can now, and is that a coincidence? Then they will, okay, maybe that's a coincidence. Let's do this for a different type of reaction. Let's do this for 100 different type of reactions. And let's do the experiments with these 100 different reactions. And let's see if all these numbers match up. And yes, it does match up. So this table could predict our delta H of our reaction. Now we don't have to do these experiments. So, you still could do them, but this is predictive of these experiments. So we got a way to calculate or predict delta H from this table. If you do an experiment like this to calculate delta H, that might take you like a couple of weeks to do it. And now you got this table, a couple of minutes. So that's pretty much that's one example of what you might, when you go to graduate school in chemistry, that's what you're going to be doing. You're going to figure out, oh, I got this table. Can this table help me predict something experimentally? So I got this table. How am I going to check if these numbers match up experimentally? I'm going to have to do these experiments and check if it matches up with our theoretical table. Would I do it once? No, I'm going to have to do this like 100 times or 50 times. And when in the lab, so that's one thing, like somebody in graduate school might have to do, make all these compounds, do all these experiments, collect all this data, and then compare it with your theoretical. If it doesn't match, oh, you got to try something else. But if it matches, you're going to be in good shape. So, we talked about bond length. Again, here's another one. Single bond. What do you think is going to have a? Well, we just mentioned triple bond. We think a triple bond is going to be tighter, right? Strong, harder to break. You think these atoms are going to be closer together? When the atoms are close together, you think you have a strong bond? Or when the atoms are far apart, you have a strong bond? What do you think?
Closer together.
Closer together, right? So now we got distance. Oh, the carbon-carbon triple bond is 120 picometer. The single bond is longer, 154. So this is another evidence that says, oh, that there is such a thing as a double bond, triple bond. That these triple bonds are actually stronger, so they should have a shorter bond length. Single bond is weaker, should have a longer bond length. And we see that with all these different examples. Triple bond, double bond. So triple bond is shorter, has the shortest, then this double bond has the second shortest, and single bond has the longest.
Professor, what are the units? Excuse me, sorry. What are the units PM?
It's like a PM and AM, right?
Uh-huh.
No, that's joking.
Okay.
It's called pico times
Oh,
10 to the
like
minus.
picometer?
Yes,
Okay,
10 to the minus 12 meters.
got it.
And we have like a little ruler to measure that. So later on, maybe next week, we're going to talk about how do we calculate these bond lengths. But right now, so we can measure these bond lengths. Right? And remember when I said California is really big in chemistry? Where do you think all this work was done in?
Berkeley.
Caltech, this work. Yep. Lewis is from Berkeley, Caltech, and this guy, Linus Pauling, bond length from Caltech. So California is really big in chemistry. So if you want to be a chemist, going to the UC schools, you'll be in good shape. And we talked about this last time. We got a table, all these bond lengths, right? Metallic bonds, shapes, right? Vesper. We talked about that last time. Does anyone have questions on Vesper?
That was how bonds are formed. So they, it dictates the model, so it avoids repulsion. Is that what that is?
Yes. So now we have bonding, right? How are these atoms going to come together? When they come together to form bonds, what's the shape of the molecule, right? So that's now we got to predict what is the shape. So water. A lot of people think, oh, water is H2O. What's the shape of water? Is it like this? Or is it like this? A or B, right?
So
What do you guys think?
tetra or triangular?
You guys talk about, you guys a little bit shaky on this. Oh, yeah. So when we think of water, go, oh my gosh, water should be linear, right? Look, H2O looks like this. But in real life, water is like this. And we go, why is it like that? Why is it bent? Tetrahedral bent. Why is it like that? And you go, what can we do to predict that it's this shape? Because this is what we see in nature, but this is kind of what we think of top of our head, but this is not correct. The top one's not correct. So now what the model we come up with is called Vesper, valence shell repulsion, right? And I'm going to skim through this because we already talked about this. So we have two atoms connected to the central atom, or two electron pairs. How could they be connected to the central atom but still be farthest away? 180 degrees, right? How can you have three atoms be connected to the central atom? What do you guys think about 3 in geometry?
Like a equilateral triangle.
Triangle. Yes. So you have something in the center, 3 atoms. These 3 atoms are occupying, the fluorines are occupying the corners of a triangle. But these fluorines are not connected to each other. They're connected to the atom in the middle. So this is called a trigonal planar.
How do they know what the central atom is every time? Is it the positive?
One way to draw the Lewis structure, and then experimentally, we could tell. So remember we talked about a little bit, what is the bond length of these atoms? If we know the bond length, then we know where these atoms are located at. So there's a way to, we could see this, a picture, we could put it through some experiments. What we're going to do is give you a little idea is we're going to shine light on this compound. When light hits something, what's it going to do? It's going to bounce off, right?
Yes.
Light's going to bounce off different directions. And based on how this light bounces off, and based on the angle, geometry, if you guys remember geometry, based on the angle and where it bounces off, we could determine where all these atoms are located at. That's called X-ray. Oops, can't spell it. X-ray crystallography. We're going to talk about that next week, but there's a way to determine where these atoms are located experimentally. So we already have the answer in the back of the book. Now we just have to explain why is it this shape. We know it's the shape. Now, why it's the shape? How could 3 atoms be connected to the central atom, but still be farthest away from each other? Trigonal planar. Then there's tetrahedral, right? We talked about tetrahedral geometry, right? That's when you connect 4 things to it. So I'm just going to skip. The next one is trigonal bipyramidal, octahedral, water. Water is also octahedral. Right? Because water, what does water have? 4 electron pairs around the central atom. So there'll be an H there, an H here. These electron pairs occupy those 2 spots. And so this water has a tetrahedral shape. But what is the molecular geometry? Molecular geometry means what is the geometry of the atoms? Just hydrogen, oxygen, hydrogen. And so this one would be called bent. But how do we get to bent? It's going to be tetrahedral. And from tetrahedral, we get to bent. So then we go there. Then there's trigonal bipyramidal, octahedral. This is a summary of Vesper. I think that's chapter 7. So this was just a real quick overview because we already covered that in our last video. So now let's go chapter 8. Advanced theories of covalent bonding. So now we got covalent bonding. We talked about the octet rule, but there's some exceptions to the octet rule. So maybe the octet rule, we need a better, what's called a better model. So a better model is something called valence bond theory. It describes covalent bonding as an overlap of half-filled atomic orbitals containing a single electron. What the heck does that mean? So let's just let's look at a picture. You can read all this on your own time. So valence bond theory is you have one valence electron on one atom, one valence electron on another one, and what they're going to do, they're going to come together. So hydrogen, hydrogen, you have a 1 electron in one s orbital, 1 electron in another 1s orbital. And what they're going to do, they're going to come together. Fluorine, 2p, it's going to look like this. They're saying this electron is going to be involved in that bonding. Not these. These electrons are already filled, so they're already not going to be involved. It's going to be this electron is going to be involved in bonding. So that one's going to interact with this one to form F2. So that's what this theory says, valence bond theory. Our covalent bonds are formed by overlap of atomic orbitals. And these orbitals have to have one electron in there. HCl, this electron, and this electron, okay? And this is our model again, what we've seen before. I'm not gonna go over this one again. Let's look at this one. SH2. Okay. We draw the Lewis structure. What does the Lewis structure says? Bam, right there. So now, valence bond theory, how is this gonna, let's try to do this for valence bond theory. So now we're gonna do our electron configuration for our valence bonds for sulfur. 3s, 3p. So this is 3s2, 3p4. Then hydrogen, 1s and 1s. So you got one electron half filled here, one electron half filled here, and these are all half filled here for the sulfur. So what's going to happen? This electron here are going to share. This electron are going to share. Right? And then what's happening when these two share? What we're going to form? SH. So this thing predicts SH2. Does that make sense? We just draw the electron configuration. Oh, we need two electrons to form a bond. Oh, this one's going to join with this one. This one's going to join with that one. Kind of makes sense. So then, this gets very wordy, but we're just going to show an example. What the heck does this mean? So let's try to extend this model to another compound. So it kind of works for SH2. Let's try for carbon and hydrogen. Based on this model, this electron and this electron, they could come together to form a bond. That means maybe there's another hydrogen out here. Maybe this electron and then this one comes to form a bond. So based on this valence bond theory, we should have this formula should be CH2. Does that make sense? Basically, this electron pairs up this one pairs up with this one. This one's paired, this one's already paired, so it cannot, it's already paired up, so it's not going to be involved in bonding. So we got CH2. What happens in real life? What is our answer in real life? CH4. In real life, we don't form CH2, we form CH4. Now we gotta say, oh, okay. Now our model doesn't work. So what do we have to do? We have to tweak it. Maybe we could tweak it and still save this model. So how are we going to tweak it? So how they're going to tweak it is, okay, what we're going to do is we're going to make one of these electrons jump it to over here. If we jump one of these electrons to here, now we're going to have 1, 2, 3, 4 unpaired electrons on carbon. So let's see how that's going to look on the next slide. Oops. Maybe not the next slide, maybe a couple slides later. So right here, this is carbon. What's going to happen is one of these electrons here is going to jump over to here. And that one electron, it jumped over there. It was over here. Now it jumped over here. Now what happens now I got 3 electrons in a 2p, 1 in a 2s. What are we going to do now? We're going to get these 4 orbitals and we're going to combine them. And when we combine them, what type of new orbitals we form? We're mixing an s and a p. How many p's are we going to be mixing with this one s? So the new orbital, go ahead.
3.
Yeah. So this new orbital we're going to form is called sp3 because we're mixing one s and 3 p's. So sp3. So now we're going to have, we have 4 orbitals on top. We're still going to have 4 orbitals, but they're going to be called sp3. We go, okay, now we have this. Now this atom, this electron could bond with this one, this to this one, this to this one, and that to that one. So they just come and they said, okay, this is how we're going to save the model. But what type of evidence do we have that this S and these P's are mixing together to form an sp3? What type of model do we have? What type of evidence do we have? So what happens is, again, what is the definition of an s orbital? Anyone remember? What's the definition of an orbital?
Was it the first two rows?
Can you say that again?
The s orbital, the first two rows?
Yeah, but what's the definition of an orbital? Why do these orbitals have a certain shape?
Was it the quantum position?
Position? Probability of finding the electrons. And how do we get this shape? We do some probability calculations, yes. That's why it has a S, like a spear shape or a propeller shape. How do we get those shapes? Is by doing math. So what are we going to do now is, like in math, 1 plus 2, 2 plus 2, we could add them up. An s orbital and a p orbital, we could add them up too. When you take like calculus 3, we could add up these orbitals using calculus. So what we're going to do is, what is the shape of an s orbital? Oops. Let me get to that slide. This is the shape of an s orbital, right? And this is the shape of a p orbital. How do we get this shape? From mathematics. These are all mathematics. We do mathematics, and that's how we give us this shape. No one just came up with that shape in the top of their head. We do the math, probabilities, and this is what the math is telling us. Because, well, how do we know do the math? Because what are electrons? Electrons behave like a what? Like a wave. Do we know the mathematics of waves? Yes, and that's how we get these shapes, because we're doing the mathematics of waves and the probability of waves. So let's extend that. Remember, we just said an s orbital is going to mix with a p orbital. Okay, when they mix, we can mix it by math. We're going to get this s orbital and this p orbital and this p orbital, this p orbital and this p orbital. And what we're going to do? We're going to add them up mathematically. And what do we get? We're going to get these 4 shapes. And what are we going to do these 4 shapes? We're going to add them all up together to give us this shape here. What does this shape here on the right look like to anyone?
Like a triangle?
What Vesper shape does it look like?
Oh, tetrahedral.
Tetrahedral. Is that a coincidence? CH4 has a tetrahedral geometry. When I add an S and 3 P's together, mathematically, it gives me this, the tetrahedral. And what do we see for CH4? Tetrahedral shape by Vesper. Now, look at this shape here. What does this lobe mean? I think someone mentioned that before. Emmanuel, what does that shape of that lobe mean? He said that earlier. Probability of finding the electron. When I have a bond, is the bond going to be out here with another atom? Or is the bond going to be right there where the electron is? Where the lobes are? Where are the bonds going to be for this atom? So with an atom way out here? No, there's no electrons there. Electrons are covalent bonds, sharing of electrons. Where are the sharing electrons going to happen? Where the electrons are. So where the atom's going to be? At these corners. of the tetrahedral. So this CH, when I get an S and I mix it with 3 P's, I get this shape, which is a tetrahedral, which matches up exactly what we see for CH4. So then when we mix an S and 3 P's, I get this sp3 hybridized orbital, this new orbital, which is hybridized, which is a mixture. And then that mixture mathematically is this one right here, which is a tetrahedral shape. I mean, yep, tetrahedral. And one hydrogen can occupy that spot, one there, one here, one there, carbon in the middle. And that's what we see for CH4. Oh, is that a coincidence? So this idea of this S and P orbitals, they're all kind of making sense now. When we add them up together, they predict the structure for CH4. Why do these two things mix? Now that's a different question, but ultimately is they want to lower its energy for some reason. When you mix these guys, it lowers the energy gets lower. So when you do this mathematically, you get this geometry right there. So this mixing of orbitals, it's happening. So when I mix, can I mix an S? Maybe here I mix an S and 3 p orbitals. Maybe I can mix an S and 2 p orbitals. That might be possible too. So this is a little diagram again for a carbon. 2s, 2p. What's going to happen? One of these electrons is going to go up there. That one goes up there. And then what's going to happen? These two orbitals are going to mix. And when they mix,
Professor, can you remind me what the ground state means?
lowest energy.
Okay, yeah, that's good. Thank you.
This is the lowest energy. But then what happens when I put an electron here? Now the electron got excited. And what happens to these two orbitals? What they're going to have? They're going to mix to form the hybrid orbital, sp3. So another way to look at this, how many orbitals are mixing here? 1, 2, 3, 4, right? What do you think about 4? What geometry do you think about 4 in a Vesper? 4 electron pairs. Oh, tetrahedral, right? So let's do another example. Let's do this. Let's mix 1s and let's mix 2 p's. We could do this mathematically. You're good at calculus. Calculus 3. Once you take calculus 3, you could do this mathematics. If you mix an s orbital and 2 p orbitals, mathematically, what you're going to get? These 3 answers. And then in real life, what you're going to do, you're going to add these 3 together. You can get that structure on the right. What does that structure on the right look like? What does this look like in Vesper?
Trigonal planar?
Trigonal planar. Exactly. Yes. Is that a coincidence mixing an S and 2 P's? So this is sp2 hybridized. Wow, this mixing an S and P orbitals, they're matching up with Vesper perfectly, right? Because if there's your central atom, where's the bonding going to happen? Over here? No, it's going to happen right here, right here, right there. That's where the electrons are, right? Trigonal planar. So this mixing S and P orbitals, the geometry matches with what we expect. Is that a coincidence? There's too many coincidences going on. So we have so many things that are coincidence. Maybe it's not a coincidence anymore. Maybe there's something behind it. Maybe this S and P orbitals, maybe they're real. Right? Because when they come up with this model, remember we talked about before, they just come up with a model. Because what is a electron? It's a wave. And we don't know where the wave is. So we have to use a lot of probabilities to determine where that wave is. And through these probabilities and some calculus, we figured out the probability is in S, P, D orbitals, right? But experimentally, we don't know if that's true or not. We just say, okay, let's assume that's true. There's an S, P, and D orbitals. Now, what we're doing now, we're adding the S and P orbitals together. And when we do that mathematically, we're getting exactly what we get. We're getting the right geometry, what we see experimentally, SP2, trigonal planar. So this
Trying to
S and P orbital,
understand. Sorry for cutting off. Trying to understand the two things. So SP2, when I see the picture, it's an overview, so that's 2D, and the other one was SP3, and that's why it's a 3D shape.
no, these are all three dimensionals. So this lobe here is it's in 3 dimensions. So think about it like a balloon. But the geometry is trigonal planar. Because remember we talked about an Vesper? How could 3 things be attached to the central atom but still be farthest away from each other? Trigonal planar. So
I was just trying to figure out how those 3 shapes turn into those 3 shapes. And
which
draw
3
it out.
shapes? These 3 shapes?
Yes.
Okay. So here we got the central atom here. Oops. So now this central atom, we're just going to overlay them. This one on top of this one, and this one on top of that one. So this lobe here might be lobe A, and that's going to be this lobe here, A. This one might be B, that's this lobe B. This one's C, that one's C. So now we're just going to get these 3 things and just put them on top, overlay them on top of each other. And when we put them on top of each other, they're going to look like this. Do you see that?
Oh yeah, I see that. Yeah. I was just trying to see how PX and YX, which one it turned to A, B, and C.
Oh, it doesn't matter because if I just PX and PY, they're the same orbital. It's just looking at it at a different point of view. These two are basically identical. It's just a matter of this. Because if I rotate it, then PY and PX are identical, just if I rotate it. So here, if I just rotate it this way, then this, if I just rotate it, then instead of this one being A, this one might be B, and this one might be A, and this one might be C. It doesn't matter. They're all the same.
Okay, thank you.
Hopefully that makes sense. So these
By
two,
next week.
okay. So we get, we mix an S and a P orbital, 2 P orbitals, we get something called sp2. And then what does that lead to? Trigonal planar. Huh. So let's figure out, let's do an example of that. Oops, let's see if I have a slide this. So we have sp2, we're going to talk about a couple of things. What do we know about sp2? We say it's trigonal planar, 120-degree bond angles because it's trigonal planar. And so let's go through an example. What does that do? So let's see if I have another slide here. Okay, let's go to this one. So now, if you focus on this one here, we have a p orbital on one atom and a p orbital on another atom. They're both px and px. When they come together, these electrons could share. And when they share, they're going to share over here. So that's kind of what we see before. When you have electrons sharing, so right here is the center of one atom, center of the other atom. We have the sharing happening right in between the 2 atoms. That's called a sigma bond. If you look at the top one, This is a PZ, so this is like the z-axis. Another PZ, this is the z-axis. And these are two atoms. So now, how could these two electrons interact with one another? They're going to interact this way. They're going to share this way. Because there's nothing here in the middle to share. They're going to share on top, and they're going to share on the bottom. So, and then once these two atoms come together, there's one atom there to form a molecule. They're going to have sharing on top, sharing on the bottom. When you have no sharing in this direct line, directly between the two atoms, and the sharing is not directly between the two, that's called a pi bond. So you still have sharing of electrons, but you only have sharing that's not in the middle. It's only on the top or the bottom. Sigma bond, the sharing is directly in between. So pi bonds are for p orbitals, p electrons. So p electrons could bond on the same line, or they could bond outside the direct axis. So it's called a pi bond, sigma bond.
They never want to bond at the very point where the two meet. They always want to meet on the, say, the side of the balloon or the top of the balloon.
For which one?
A pi bond and the other one, how they just don't actually meet at the 2 points where they come together in the, say, like x orbital and p orbital, how they come to a fine point and touch. They want to largest points.
Largest points. I'm not sure what you're.
Like the rounder edges instead of like the fine point, how the two on the other side like to come together, just touching the tips, and the other ones want to touch the rounder end of the balloon.
Oh, okay. So you're talking about just the sharpness of it or the roundness of it?
Yes.
So again, what does this mean? The shape of this, what does the shape represent? Nope. Ask Emmanuel, what does that shape represent, Emmanuel? Probability of what?
Of location of electrons.
Electrons, right? That's all these shapes are. Where is this electron? Probability of finding that electron. And how do we determine this probability? Through these mathematical type of models, probability models. And if you talk about the sharpness or the roundness of the edge, that's what the math tells us. So I can't really comment on that, but these orbitals, I wouldn't focus on like the the sharpness or the roundness, just where the electrons are located, top and bottom. Here on the bottom, along the same axis, pi bond on top and bottom, not in the middle. Which one you think is a stronger bond? The pi bond or the sigma bond?
Sigma?
Something we have a direct connection between one nucleus and another nucleus, something that's a direct line in between, something that's on the side. What do you think has a stronger bond?
Sigma.
Yeah, sigma bonds. I mean, we could determine that experimentally, but yes, sigma bonds are stronger.
So you mentioned that pi bonds were on the p orbital. So the sigma bond is also on the p orbital?
How many p orbitals do we have in an atom? Any atom.
Remind me.
Why do we call it px? Why don't we just call it p? Why do we say px? Why do you say py?
That varies on the axis.
Why do you say pz? So how many p orbitals do we have?
Three.
3. And one way to draw it is from one atom, the p p orbitals are lined up on the same line. Another way is the p orbitals are not lined up. Right? You've got a p orbital that way, a p orbital this way, p orbital coming out of the board. So when I have two of these coming up, it's going to line up like that. When I have two of these lined up, they're going to look like that. And they come together. So pi bonds only happen when you have your p orbitals, I guess we call it orthogonal to each other, like this. When the p orbital is like this, we're going to have a sigma bond. So sigma bonds are for p orbitals and sigma, and for s orbitals.
Okay.
We can talk about d orbitals too, but so p bonds, p orbitals could involve in sigma bonds and pi bonds. Because we have three p orbitals, so one set's going to go this way, two sets are going to go this way. What does that all mean? So this gets pretty wordy. What we just mentioned before, sigma bonds are stronger than pi bonds. And all of this we're going to talk about soon through an example. So here's this structure. This is called formaldehyde. And what's happening here is, if you draw the Lewis structure, we got a double bond here. What the heck is, what does double bond mean? Double bond means you have, so if you look at this carbon here, this carbon, this is what geometry is this one? What's the geometry of this structure? Anyone? T? What does T mean? Tetrahedral? Nope.
Trigonal planar.
Trigonal planar. Because even if you have a double bond there in Vesper, that represents just one group. So here, carbon has 1, 2, 3 groups around it. So that's trigonal planar.
Oh, okay. So that double bond there, it's when we're looking for the shape, it still counts as one bond, but it just happens to be a double bond or a triple bond, but it's still one bond there.
Yes.
Okay.
Yep. So this is 3 groups. So then we have a trigonal planar. And trigonal planar, what is that? sp2 hybridized. So what do we have here? Oops. Let me see my pen. Where's my pen? Oh, my pen's over here. Why do we have, how do we explain this double bond then? That double bond is a carbon. This is the sp3 hybridized orbital for carbon. This purple one is sp3. So one of these is going to interact with the p orbital of oxygen. And that's going to result in sharing of electrons right in the middle. That's a sigma bond. But the oxygen also has a p orbital. And the p orbitals are, okay, red and red doesn't work. So the p orbital is also over here. And this carbon also has p orbitals. So then you're going to have these p orbitals interacting. So you get a sigma bond and you're going to have a pi bond. So the ones on top up here, oops, are pi bonds. Yeah, sorry, colors don't match up really well here. It's hard to see. But the sigma bond's the one in the middle, and you get a pi bond also going on. So one of these, so you have a double bond. One of the bonds is a sigma bond. The other bond is a pi bond. So whenever you have a single bond, that's always a sigma bond. So always these, when you have a single bond, it's always a sigma bond. When you have a double bond, one's going to be a sigma bond, one's going to be a pi bond. So a double bond, what is a double bond? One is going to be a sigma bond, the other one's going to be a pi bond. That's what makes a double bond. So this is what we see graphically. And one of the bonds is a sigma bond, one is a pi bond.
Sorry, could you summarize that? A sigma bond is always single?
All single bonds are all single bonds
Okay,
are sigma.
or sigma.
Double, one is a sigma, one is a pi.
Thank you. 1 sigma, 1 pi.
I think this is the same slide. So look at this one.
Professor, sorry, what would a triple bond be then?
Well, we're going to get there. We're going to get there. We're going to get there. But basically,
Okay.
with a triple bond, one sigma, 2 pi, or 1 pi and another 1 pi. Because remember, how many p orbitals are there on oxygen? For any atom, how many p orbitals are there?
3.
3. I'll put my oxygen, one atom, one p orbital is going to look like, one p orbital is going to look like this. And it's going to line up directly with another atom. That's where we're going to get our sigma. Where's the other p orbital going to be? One's
Above
going to
it?
be on top, and another one's going to be coming out of the board. So you can have one of these p orbitals for one pi bond, another one for another pi bond, and we'll show a picture later on. So basically, the other for triple bond is going to be a sigma and 2 pi bonds. But we'll get there. So look at this compound here. What do we have here? A single bond. And what we notice about single bonds is single bonds could rotate. Right? Single bonds could rotate. What does that mean? Let me write the structure a different way. You see the difference between how I drew these two structures? Is there a difference how I drew it? Anyone notice?
Chlorine and hydrogen are flipped.
Yep, they're on opposite sides here, right? But both of these compounds, how I drew them, they're identical. Why? Because a single bond, I could have rotation. So this whole group here is rotating. So when it's rotating, this eventually or spinning, this chlorine is going to be at the bottom. It's constantly spinning. So I think that's what this picture here is trying to show. That this bond here is rotating. It could rotate. So the chlorine could be at the bottom, or it could be at the top, or it could be in the middle. It's constantly rotating. It's called free rotation. So single bonds, they could rotate. When you have a double bond, see how this one's on the right, how it's drawn? Chlorine on the bottom, this chlorine on the bottom. These two compounds I drew, they're completely different compounds. The chlorine, because we're on a double bond, this bond doesn't rotate. No rotation. So it's hard to rotate when you have a double bond. So a single bond, they rotate. Double bond, no rotation. So this is like fixed, locked in place. This one, rotation. Single bonds can rotate, double bonds cannot rotate. So look at these two compounds here. This one's called cis This is called trans. Why do they call they're the same compound? They're isomers. Remember what isomers were? Anyone remember? What is an isomer?
They have the same chemical makeup, but it's a different molecule. Did I say that backwards?
You're on the right track. Just your wording's a little bit off, but yes, same formula.
Same formula.
Yes, but
Different.
different. You could be either different connectivity or different arrangement in space. So here, the same formula, but the chlorine's down here, chlorine's up there, and these are two different compounds. And we call this one cis and trans. Trans means like they're on opposite sides. And cis means they're on the same side. Because why are they two different compounds? Because there's no rotation. So if you actually look at these two compounds, they actually have different properties. They have different boiling points, different reactivities. So now let's talk about sp. And sp, let's see if I have the model here. If I have an s orbital and a p orbital, let's do this mathematics again. Do our calculus, get an s orbital and a p orbital. Let's add them up together. And what do we get? This geometry there. What geometry is that?
Linear.
Linear, which matches up with the Vesper, right? So in Vesper, we have linear, trigonoplanar, tetrahedral. And what happens? When we add the s and p orbitals, we get this linear, trigonoplanar, tetrahedral. So when we add an s and a p, what type of geometry you think you're going to get when you add an s and a p orbital together? Linear. So if you just look at this slide, this is just a little brief introduction on what's going to happen on the next slide. But if you have a triple bond, one of the bonds is going to be a sigma, the other two are going to be pi bonds. And we have something that's linear, it's going to be sp hybridized. So what the heck does that mean, sp hybridized? So look at carbon, electron configuration for carbon. And then we go, what is going on? How is this hybridization going to work for this type of molecule? So a lot of times this hybridization, we already know what the answer is. We know what the shape is. Now this hybridization, say, okay, how are we going to mix them up so we could justify this shape mathematically? So we already know what the shape is. So what we're going to say is, this is before hybridization. This is what we have. And what we're going to do is we're going to do a couple of things. Oops. We're going to get this electron and make that electron go over here. And that's what happened over here. We made this electron jump to over there. So now we got a situation like this. And this is the carbon, and this is, one of these carbons here. Now, how many bonds does this carbon have? Basically 4 bonds, right? 1, 2, 3, 4. So how are we going to form these 4 bonds? So from here, we're going to say that one S and one P are going to mix. We're not going to have an S and three Ps. We're not going to have sp3. We're just going to have this and this one mix by themselves. And then these two are not going to mix. They're just going to stay by themselves. So we're just going to have these two mix. When these two mix, what are we mixing? One S and one P. So we're going to have an sp hybridized. Then the other two that didn't mix, they're going to stay the same. They're going to still stay as a p orbital. They didn't mix. So if you look at this picture on top, this is our carbon here. What's going to happen is the sp, what's the geometry on sp? What do we say what's the geometry on sp?
Linear.
Linear. So that sp is going to be involved in interaction with this carbon over here to form a, and this hydrogen over here forming a linear arrangement between this hydrogen, this carbon, and this carbon over here. So this sp is right there, that pink part. Then these other two p orbitals for carbon, they're just going to stay as a normal p orbital. You get this p orbital up here, a carbon. And then this carbon also has a normal p orbital. So what happens when a p and p come together? They're going to form a pi bond. So on this model, an s and a p are going to come together to form an sp hybridized orbital, and this sp hybridized orbital is going to result in this linear arrangement right here, this one and that one. That's what this sp is going to be doing. Then these other two p's that didn't mix, they're just still two p's, they're still the p orbitals on this carbon and this carbon, and when they mix, they're going to form a pi bond. Oops. And how many p orbitals we have? Two p orbitals. So one's going to be one pi bond, and another one's going to be involved in another pi bond. So go, what the heck is going on here, right? It's because what happens is we already know the shape of this molecule. It's linear. So how do we tweak this hybridized model? So the only way to make sure this we get this linear compound is only this S and this P are mixing. And then these two here are not mixing. So that's a big flaw in this model, because we have to look at the answer before we could understand, why is this S only mixing with one of these P's? How come it's not mixing with all three? Because we already know this shape is linear, so it has to be mixing this way. So that's one of the flaws of this model. So we notice that this model has some flaws. So now we got to find a better model. But this model kind of tells us a little bit of information that there's this S and P orbitals are mixing. And when they mix, they're going to lead to a certain geometry of the molecule, right? So here's the central atom. If it bonds, where's bonding going to happen? Over here and over there. Why in these two spots? Because that's where the electrons are. Electrons, that's where bonding happens, where the electrons are. Is it going to have bonding out here? No, this molecule doesn't have bonds, doesn't have electrons out there, so there's not going to be any bonding there. So this idea of mixing S and P, and mathematically we're getting the right geometries, that tells us that this S orbital, P orbital, they are real. There's such things as S orbitals and P orbitals, even though we can't see with our eyes. Because the electron is so small, we don't have like an equipment to see the electron. It's too small. But mathematically, we predict what the shape of these S orbitals and P orbitals are, and they lead to this, the correct geometries when we mix them. SP, SP2, SP3. So just to give you an idea, SP, when we mix them, what's going to give us? Something that's linear. SP2, trigonal planar. SP3, tetrahedral, right? So one simple way to remember is, okay, S and P, how many total orbitals I have? One S and one P. So that's a total of what? 2. How could two things be connected to the central atom but still be linear? But sp2, we have one S and how many P's? 2 P's to give us a total of 3. What do we think about 3 in Vesper? Trigonal planar. sp3, how many total orbitals we have? 1s, 3p. That's a total of 4. What do you think about 4 in Vesper? Oops.
Tetrahedral.
Tetrahedral. Oh man. Sorry, I think I'm having problems with this thing. Oh. I lost my pointer and marker. Oh, okay, got it back. So SP, 2 orbitals, linear, SP2, 3, trigonal planar, SP3, 4, tetrahedral. Okay? So this all makes sense. We already know about linear, trigonal planar, tetrahedral. Now when we do the mathematics of SP, SP2, SP3, it leads to these same geometries. You think that's a coincidence? No, it's not a coincidence. So here's this compound, ethylene, or acetylene. We got this compound, one of these bonds, sigma bond. These other 2 are going to be pi bonds. So the red ones, so the purple one's a sigma bond, and these 2 red ones are going to be pi bonds. So in a triple bond, 1 is going to be sigma, and 2 of them are going to be pi bonds. All right.
In that picture you just showed, there was 4 red pieces in general. Oh, because each of them connect together. That's why.
Yep.
The sigmas connect. Okay, thank you.
Okay. So that's why this triple bond or single bond, there's no rotation because you can't be twisting these pi bonds. If you twist them, they're gonna, you can't twist them. So you have no rotation on a triple bond or double bond. So here's an example, BeCl2. If you look at Be, what's the electron configuration? 2s. And what's going to happen? This electron is going to jump up, or one of the electrons is going to jump up, and then they're going to mix, hybridize. When they hybridize, you're going to have sp and sp to an sp. And then this is going to open up space for you could have bonding with your 2 chlorines. So how hybridization works, an electron gets promoted, moves to an empty orbital, then these 2 orbitals are going to mix, and that mixing is called hybridization. And you can have 1 electron in each hybridized orbital, and that allows room for 1 more electron to come in for bonding. So this is our valence bond theory. So now let's do this. Let's see if I have this shape here. So remember we said we mix an S and 3 P's. What do we get? Tetrahedral geometry, right? How about if I want to mix an S, 3P? How about if I want to put in 1 more orbital to mix in there? What's another orbital I could put in there to add on to this? What other orbitals do we learn about? There's an S orbital, a P orbital. What else do we learn about? What other orbitals are there?
D and F.
What was that?
D, F.
D. So now there's no more P orbitals to mix, right? 3 maximum. There's only 1 S orbital. Let's mix an S, 3 P's, and 1 D mathematically. And let's see what we get. You know what we get? What shape is this on the right? In Vesper, what shape is that? Oh, you guys forgot your shapes already?
Is it trigonal still?
So if I have, well, let's go through. What is it? So Vesper, there's linear. What's after linear?
Trigonal, then tetrahedral.
Trigonal planar, then tetrahedral. What's after tetrahedral?
pentagonal.
Bipyramidal.
Ooh.
So when you mix an S, 3 P's, and 1 D orbital, mathematically, what do we get? Trigonal bipyramidal, which matches up exactly with Vesper. You guys follow me so far? Is that a coincidence? I don't think so. Do you remember what trigonal bipyramidal is? You draw a triangle here. There's an atom on these corners. Your central atom's here. You're going to get an atom up top and an atom on the bottom. So here you got your essentially you got your triangle there. One up, one down. So this is just, not doing an experiment. This is just doing the math, mixing an S, 3 P's, and 1 D, and then match up with our Vesper, trigonal bipyramidal structure. So sp3d, so we're mixing 1 S, 3 P's, and 1 D. That leads to trigonal bipyramidal. We talked about that when we talked about Vesper. Oops. Let's extend that. Let's have instead of mixing sp3d, let's do one more time. Let's mix an S, 3p, and then instead of 1d, let's mix 2d's in there and see what happens. So we're going to mix an S, 3p's, and 2d's. What are we going to get? sp3d2. Mathematically, when we mix all those orbitals together, called the wave function in calculus, and do some probability, and what structure we get here? Octahedral. Okay. And what's the shape of octahedral in Vesper? Basically, we have a square, atoms on the square, a central atom, one atom on top, one atom on the bottom. And that's what we have here. We have a little square there, one atom on top, one atom on the bottom. So then we hybridization, we're mixing these orbitals, it leads us exactly to the structure of their compound. Because where can we have bonding? Where electrons are or where the electrons are not? It's where the electrons are. So atoms are going to occupy these spots or these positions, and that is a tetrahedral. So this hybridization, mixing these orbitals, leads us to our Vesper structures. So here's another, this is an example of a octahedral, sp3d2, that leads to octahedral. What does octahedral mean in Vesper? It means 6, right? We go 1, 2, 3, 4, 5, 6. sp3, how many orbitals are we mixing here? 1s, 3p, 2d, and that equals to 6. 1, 3, 2 equals to 6. What do we think about 6 in Vesper? Octahedral. So this is just a table summarizing the hybridization. We have 2 electron groups around the central atom. Vesper tells us that's linear. And when we mix an S and a P, hybridization tells us that's linear. 3 electron groups, Vesper tells us that's a trigonal planar. Hybridization, sp2, also tells us it's trigonal planar. Right? It matches up. 4, tetrahedral for Vesper. Our valence bond theory, hybridization tells us it's tetrahedral too. So valence bond theory, hybridization, a match again. 5, mathematically, let's mix sp3d we get the same structure, trigonal bipyramidal. Octahedral, mix these guys, octahedral. So is this all a coincidence that this all matches up? Mathematically, we're just adding up an p orbitals, sp2, sp3, and so forth, and it lines up with these VSEPR structures, or the real structure what we see in real life. That's probably not a coincidence. That's probably, there's something to this s and p orbitals. So this, along with other evidence, tells us this s orbitals, p orbitals, they are real because they predict the structure of our compounds. So hybridization, we always have to do, what do we have to do? We always have to draw the Lewis structure, understand the VSEPR. Once we understand the shape in VSEPR, then we know what the hybridization is. Because if we know the shape, then we know the hybridization. Because the shape is really, they're all related. If I VSEPR, I know it's tetrahedral, now I know it's sp3 hybridized. If it's bipyramidal, trigonal bipyramidal, I know this hybridization. If it's octahedral, I know it's this hybridization. So basically the easiest way to know what the hybridization is look at the shape by VSEPR, and then once you know the shape, you know the hybridization. You could go the reverse way, know the hybridization, and then know the shape, but that's a lot more difficult. So know the shape first, and then from the shape, you know what the hybridization is. And then if it's a single bond, sigma bond. If you have a double bond or triple bond, then we have pi bonding. If I only have a single bond, it's always going to be sigma. If I have a double or triple bond, then the second or third bond is going to be a pi bonding. So now, this valence bond theory looks pretty good, but what we notice, one thing is there's some gaps with this valence bond theory. And one thing we notice is, if you look at this, one thing we know about oxygen, O2, is that oxygen is magnetic. And we'll talk about this a little bit later, but when it's magnetic, that means you have to have an unpaired electron. You can't have paired electrons. You have to have at least one unpaired electron for it to be magnetic. And we go, but valence bond theory predicts O2 is going to have all the electrons are going to be paired up. There's no unpaired electrons. So valence bond theory, it's better than Lewis structure because it tells us a little bit about bond strength, because it tells us about pi bond, sigma bonds, tells us about the rotation of the bonds. But there's some gaps. So one thing what it doesn't tell us is like a compound like O2. In real life, we know O2 is magnetic or slightly magnetic, but this valence bond theory doesn't predict that. So now we go, maybe there's a better model than valence bond theory to predict bonding. Valence bond theory is pretty good, better than Lewis structure, octet rule, but maybe we can improve upon it a little bit better. Is there a model that could predict that oxygen is magnetic? And that's the next step is, okay, let's valence bond theory, let's improve upon that. Let's get a better model. So now we're going to go into this topic of molecular orbitals. So we talked about atomic orbitals, right? Everyone remember what atomic orbitals are? Orbitals from the atom, s orbitals, p orbitals, d orbitals. But now when we have a molecule, what are these s and p orbitals going to do? They're going to mix with each other and then form a new orbital, which is called a, now when we talk about orbitals and molecules, we're going to call them molecular orbitals. So now, when electrons are in molecular orbitals, what do? How many molecular orbitals are there? Right? what are these molecular orbitals? And that's where we're going to get into the next couple of slides. Does anyone have any questions so far? Everyone shocked? Stunned?
Yes.
All right. This is just the beginning. All right. So this might be a good place to take a little break. Let's take a 10-minute break. Let's meet back at 9:50. We'll see you in 10 minutes. So we've got molecular orbitals. Where do molecular orbitals come from? They have to come from atomic orbitals. What are atomic orbitals? S, P, D. So these orbitals, when these atoms, these orbitals interact or combine, they're going to form molecular orbitals. And what do we know about orbitals? They are probability of what? Finding the electron. And how do we do the mathematics of probability of finding this electron? It's because electrons behave like a wave, right? And do we know the mathematics of waves? Yes, we know the mathematics of sine, cosine. We know all this type of high-level math on waves. So we're going to apply that mathematics on waves to understand molecular orbitals. So where are molecular orbitals going to come from? From atomic orbitals. We're going to combine atomic orbitals. And then that's going to lead us to a molecular orbital. How are we going to combine them? Just like what we did for S and P in hybridization, sp3, we combine them and we got the shape. But what do we know about these orbitals? These waves? When these orbitals come together, what happens when waves come together? They could add constructively or they could add destructively, right? Remember our model of a wave? When waves come together, we could add them constructively or destructively. When they add together these waves, then we got bonding. When they don't, when they cancel each other out, then we got no bonding. So constructive, destructive, these electrons could come together constructively or destructively. When they come together constructively, we call that a bonding orbital. And what's an example of a bonding orbital? We just talked about before, a sigma bond, pi bond. When they come together destructively, we call that a anti-bonding orbital. So what type of anti-bonding? You know, there's still going to be sigma and pi, but we're going to put a little star on top to tell us it's anti-bonding. So there's going to be bonding orbitals and anti-bonding orbitals. Why are we calling those things? Because waves could come together constructively or destructively. That's just what we see in nature, right? So these orbitals, when these waves come together, so let's look at this one on the bottom, an s orbital and an s orbital. When they come together, they could come together constructively or destructively. When they come together constructively, they're going to have sharing of electrons. And we're going to call that, bonding orbital. And again, these are waves, right? So when they come together, they could come together constructively, add together, or they could come together destructively and subtract each other out. When they come destructively, there's no sharing of electrons, and that's called anti-bonding orbital. This little star. So there's going to be a lot of orbitals coming together. So how do we know which orbitals are we talking about? Here we're going to be talking about the sigma 1s. What type of bonding do we have here? Electrons are being shared in the middle. That's called the sigma bond. What electrons are being shared? The 1s orbitals are being shared. How about here? Anti-bonding, it's the sigma star, and it's the 1s orbital. Oops. that it's, any questions so far? We're good, we're good. So these orbitals could come together constructively or destructively. When it's constructive, that is when we have bonding. Destructive, we call it anti-bonding. Okay, so what does that all mean? So when we add them together, the electrons are in bonding molecular orbitals. That means these electrons are being stable. If the electrons are in anti-bonding orbitals, they are not stable. So if you're stable, are you at higher energy or you're lower energy if you're stable?
Lower.
Lower. If you're not stable, you're at higher energy. So remember how we fill on electrons in a s, like a electron configuration? When the s orbitals are filled, then we fill up the p orbitals. Why do we have an order how we fill up these electrons in these orbitals? Based on whichever one has the lowest energy, that's where the electrons are going to go. When those orbitals are filled, the electrons are going to go to the next highest one, or next lowest energy, and the next lowest energy. So basically this slide is telling us that bonding orbitals have lower energy, anti-bondings have higher energy. So when we have say an s orbital and s orbital, there's two possibilities, constructive and destructive. So when these two s orbitals come together, if they form a bonding orbital, what's going to happen to the energy? Energy goes down. What happens to the energy of an anti-bonding? It's going to go up. So, and there's something called a node. What does a node mean? The probability of there being an electron. When the probability is 0, then it's called a node. So here, is there any electrons between this atom, between these two atoms? No. So that's called a node. Oops. So bonding orbitals, lower in energy, anti-bonding, higher in energy. How many electrons could go into this s orbital here? Maximum. 2. Here, maximum 2. This one, how many maximum electrons could go into this orbital over here? 2. How about up here? 2. So these molecular orbitals, kind of the same rules as atomic orbitals. I could have a maximum of 2. Maximum of 2. See, someone left a comment here. Do we have an exam next week? I don't know. I have to look at the syllabus, but I think so. So yes. So we'll talk about the syllabus after this this chapter. So now we're going to say, okay, there could be electrons here, and then there can be electrons up there. So how do we know if this thing forms a bond, or how many bonds are we going to form? So there's something called the bond order. Number of electrons that are in the bonding orbital and number of electrons in anti-bonding orbital divided by 2. That's going to give us something called the bond order. And let's figure out what the heck does that mean. Here's a terminology we should talk about. We'll talk about it later too, but oops. When something is, when you have unpaired electrons, that's called paramagnetic. So paramagnetic means basically we are magnetic when you have unpaired electrons. Then let's look at this one here. We got a hydrogen atom here, 1s and 1s. And when they come together, so this is your atomic orbital, 1s, and you have another atomic orbital over here with this other hydrogen, 1s. When they come together, when 1s and 1s come together, what could happen? You can have a bonding orbital or a anti-bonding orbital. So that's what we're going to draw here. When that 1s and 1s come together, we can form a bonding orbital, We just draw it as a little box. And we could have an anti-bonding on top. Why is anti-bonding higher in energy? Because anti-bonding is not stable, so it's higher in energy. Bonding orbital is lower in energy. So what's going to happen? So we're going to form a bonding orbital and anti-bonding molecular orbital when these two atoms come together. When they come together, how many electrons could come up be at the bottom? Maximum of 2. So where are these electrons going to go? Like a 1 electron there, 1 electron there. Where's that electron going to go? Is it going to go up right there to the top one? Nope. Where do electrons want to go? To high energy or the low energy? They're going to want to go to the low energy. That's why the 2 electrons are in the bonding orbital. So now, what is the bond order for this compound? H2. Let's see if I got. Oh, excuse me. So what's the bond order? Bond order is going to be number of electrons in our bonding orbital, 2, minus how many in our antibonding, 0, divided by 2, that equals to 1. So this predicts that H2 is going to have a bond order of 1. And in real life, when we do the Lewis structure, yes, H2 has a single bond. Okay, did we get lucky there? Let's see. That's just a coincidence. Let's do another one. Lithium. Here's lithium. We put the 2s. We're just going to put the valence electrons because what does the chemistry? The valence electrons are the core electrons. The valence electrons. So we're going to focus on the valence electrons. So we have 1 electron in the s orbital, 1 electron in this s orbital. When they come together, 2 electrons here. Pretty simple. What's the bond order? Same as before. 2 minus 0 divided by 2 equals to 1. So the lithium predicts there's a bond order of 1. All right. So now, look at this. So we're focusing on s orbitals coming together. But s orbitals could come together, but what else could come together? P orbitals could come together. So here's a picture of a p orbital. And p orbitals come together. And just they're like, what is p orbital? Probability of finding an electron. So when p orbitals come together, they could form something called a bonding orbital and a anti-bonding orbital for p orbitals also. So how does this p orbital look like when they come together to form bond? Oops. A px and a pux, they're both lined up on the same axis. So when they bond, you're going to lead to a sigma 2p. When they don't, now the anti-bonding is going to look like kind of like this, no bonding. So you have a bonding orbital, anti-bonding orbital for this 2p orbital. Why do we call it sigma? Because look at the electron sharing. Electrons sharing right in between the 2 atoms. Now, there's other p orbitals, right? pz, pz. And they're lined up kind of like orthogonal to each other. But then they could have also lead to a bonding orbital or a anti-bonding orbital. And how's that going to look like? What type of bonding we're going to call this one? The bottom on the bottom one is that it's a bonding orbital, but is that a sigma bond or a pi bond? One on the bottom. Pi bond. And what are we talking about? The two p orbitals. And with that anti-bonding, it's going to be a pi star. So there's another p orbital, right? These atoms have 3 p orbitals. So one of the p orbitals could be involved in sigma bond. This p orbital can be involved in pi bond. There's another p orbital. And this is coming like out of the page. So they're going to interact this way. So I can have a pi bonding, and I could also have pi star one. So when the p orbitals interact with each other, I can have 1 sigma and 2 pi bonds. So now let's draw this picture. So this is the atomic orbitals. So these are like the atoms, right? What we see before. 2s, 2p. And another atom, they also have a 2s, 2p on this side. And what they're going to do, these orbitals are going to interact with each other. So this is what we did before. 2s orbital is going to interact with this 2s orbital. This 2p is going to interact with this 2p. And what we just talked about is when they interact, we're going to have sigma bonds and pi bonds. So look at this. When I have an s orbital here and this s orbital, I got 1 s orbital here, 1 s orbital here. What's that going to lead us to? 1 molecular orbital, 2 molecular orbitals. See that? So the number of atomic orbitals is going to equal the same number of molecular orbitals. So now, look at this 2p up here. I got how many boxes? 1, 2, 3, 3 orbitals. This one I got 1, 2, 3. So I got a total of 6. 1, 2, 3, 4, 5, 6. So when these orbitals come together, I can form pi bonds, sigma bonds. If I found bonding orbitals, I might form anti-bonding orbitals. And what happens in certain situations, the pi bond is lower in energy than the sigma. In other situations, the sigma bond is lower in energy than the pi bond. So I'm just going to make up a situation here. I got these 3 electrons. Where are these 3 electrons going to go? In here. Are they going to go like this? 2 on top, 1 on the bottom? Go like that. 1, 2, and then the third one up there. 3. How about we have something like this? 2 electrons here, 2 electrons here. Where are those 4 electrons going to go? 1, 2, 3, 4. How about have 5 electrons? Oh, then the 5th one has to go there. So this is how we're going to, atomic orbitals, they're going to combine with another atom and they're going to form molecular orbitals. And these orbitals are going to have a sigma or pi bonding. And how do we fill in the electrons? From the lowest to the highest. So back to our question. Oxygen is paramagnetic in real life. We know that. We could do the experiment. This is basically like a magnet. You put in liquid oxygen, and then the oxygen is magnetic. So oxygen is something called paramagnetic. And what this paramagnetic means, you have unpaired electrons. Something called diamagnetic means you have all the electrons are paired. Paramagnetic means you have some electrons are unpaired. But diamagnetic means all the electrons have to be paired up. So oxygen is paramagnetic. There's some unpaired electrons. But the Lewis structure, valence bond theory doesn't predict if something is paramagnetic. Right? What is the Lewis structure of oxygen? It's just like this. There's no unpaired electrons. Everything's paired up. So Lewis structure, valence bond theory doesn't predict that oxygen is magnetic. So let's see if this new theory of molecular orbital theory will predict if oxygen is magnetic. So this is our valence bond theory. We got a sigma bond, we got a pi bond, all right, but there's no unpaired electron. So let's see if I got this would be, I gotta use this one. So let's look at this one. This is oxygen here. What are the atomic orbitals for oxygen, electron configuration for the for oxygen, 2 electrons in the 2s orbital, 4 electrons in the 2p orbital, right? This is something we know already. This oxygen, same thing, 4 electrons here, 2 electrons here. And what's going to interact? This 2s orbital is going to interact with this 2s orbital. And what are we going to have? Molecular orbitals. These are our molecular orbitals for O2. And then what we're going to do, we're going to fill them up. So here on the bottom, I got 2 electrons here, 2 electrons here. So how many electrons should I have here? 2 on the bottom, 2 on top. How about here? I got 4 there, 4 there. How many electrons should I have here? Total of 8. 1, 2, 3, 4, 5, 6, 7, 8. What is the bond order for this compound? Anyone can give me a number? Bond order?
Is it 1? Is it 4 minus 2 divided by 2?
Yeah. Just type in a number. It could be. We're going to work it out. I just want to see what people are getting. Oops. Somebody's saying 1. Oops. So bond order means bonding electrons minus anti-bonding electrons, right? So how many bonding electrons do I have? 2 and 6. That's 8. Minus how many anti-bonding? 2 there, 2 there. That's 4. Divided by 2. So the answer is 4 divided by 2, which is 2. So the bond order is 2. What do we know about O2? It is a double bond. Lewis structure O2. Double bond. We got a bond order of 2. Does that predict the bond? Oxygen? Yes. Is oxygen diamagnetic or paramagnetic?
Download the.
What do you guys think? Paramagnetic or diamagnetic? Let's go back. What is the definition for paramagnetic? Unpaired electrons. Do I have any unpaired electrons in my molecule? What is my molecule? O2. That means I have to look at everything over here. Do I have any unpaired electrons anywhere? Right there. I got unpaired electrons. So this is paramagnetic. So this model predicts I have a bond order of 2, double bond. It predicts that oxygen is magnetic or paramagnetic, and that's what we see in real life. So this model predicts the bond order and predicts it is magnetic, which Lewis structure, octet rule, valence bond theory, hybridization cannot predict. So this molecular orbital theory predicts it is magnetic. So which are the anti-bonding orbitals? Anti-bonding orbitals are ones that are higher in energy, the ones that have a star. And it's hard to see it, but there's this little star on top. These have little stars. Anti-bonding. These guys are anti-bonding. So, and this might be a better picture of what's going on. This might be in your book too. These are your anti-bonding, the ones with the star. All right. So now we could combine atoms. In this case, we combine atoms that are identical. But we could have, I'll combine atoms that are not identical. So here's an example of what we could do. Combine a nitrogen and an oxygen. So why is the oxygen 2s lower than the energy than the nitrogen 2s? Typically what we see is that the more electronegative the atom is, the lower the energy is. So these are two different atoms, so they're going to have two different energies. So they're not going to be equal energies. So in this situation, what's going to happen? The s orbitals on the nitrogen is going to interact or combine with the s orbitals on oxygen. P orbitals on nitrogen going to interact with these p orbitals. And what we're going to do, we're going to fill them up. 2 electrons here, 2 electrons here. We're going to have 4 electrons in the middle. 4 electrons here, 3 electrons there. Let's fill it up. And 1, 2, 3, 4, 5, 6, 7. So what's the bond order for this compound? So why don't you guys calculate that? Bond over 5. Everybody has a number? Too difficult of a question? Or see how many more slides we have left? Oh, we're almost at the end. Maybe we have time for a quiz.
I don't think so. I feel a lot of questions coming on.
All right.
No, this is actually a little bit confusing, but I see what you mean. But it needs practice.
Needs
I
a lot
didn't
of
do
practice.
chapter 8 homework yet.
Needs a lot of practice.
This
This
is
is like
basically like a foreign language.
yep. We're trying to understand how bonding works. So this is like this is pretty much the most up-to-date model, the most accurate model we have for bonding is this molecular orbital theory. So what is the bond order? Bond order is number of electrons in bonding orbitals. How many electrons do we have in a bonding orbital? Got 2 there, 6 there. So we got 8. Everyone see how we got that 8? how many electrons do we have in anti-bonding orbitals? Oh, here's an anti-bonding. Here's an anti-bonding, so 8 minus 3 divided by 2. So that's going to be 5 divided by 2. So that's, is that right? 5 divided by 2, that's about 2.5. Yep. So what this predicts is we have like it's a bond between a double bond and a triple bond. NO. All right. Is this compound paramagnetic or diamagnetic? Oops.
Diamagnetic.
All right, let's look at the definition for diamagnetic. All materials, oops. Material that has all electrons are paired up. All electrons are paired up. Are all the electrons paired up in this box?
Not above the pi.
No. There's something there that's not paired up, right? So is this paramagnetic or diamagnetic?
Para.
Para. Yep. I know this
I thought you didn't count that one.
I know it takes a lot of time. This is pretty much the most confusing thing in general chemistry. How do these atoms come together to form a molecule? And then these molecules are going to have its own orbitals. And where do these orbitals come from? From the atomic orbitals. And then these electrons are going to fill in from low energy to high energy. And there's something called bonding orbitals, and there's something called anti-bonding orbitals. Because why? Because electrons behave like a wave. And when they behave like a wave, they could add constructively, otherwise known as bonding orbitals, or they could add destructively, otherwise known as anti-bonding orbitals. Anti-bonding are not stable.
And in a problem like this, it always indicates the anti-bonding, because otherwise how would we know?
So p orbitals could interact with p orbitals to form a bonding and anti-bonding, or they could form to form pi bonding and a pi anti-bonding, or a pi bonding and pi anti-bonding. So that's how we get all these boxes from this previous slide I just mentioned. Is for p orbitals, they're going to be 2 pi and 1 sigma bond. And then which one's going to be lower in energy, bonding or anti-bonding orbitals? Bonding orbitals, right? Anti-bonding is going to be higher in energy. So these are the things you have to remember. And then,
So sorry, on that last slide 42, could you explain to me the reason why there was one on and there was 2 on the other?
on this one,
2 slides up. Sorry, maybe one more. It was when you were just showing the 2 graphs that were side by side.
oh, these two?
Yeah. There's a P2 and on the other side there's a pi P2. Why is it? Because it's a straight line and the other one's the connected.
Can you say that again?
The one's a sigma on the left, I believe, and there's a pi on the right. Is that because the one on the right there, how there's 1 space for it, and the other side there's 2 spaces?
Okay. So here they're reversed.
Okay.
Here the sigma's top, the pi's on the bottom, this one on the right, they're reversed. So sometimes it could be reversed in terms of the energy. One could be lower in energy than the other one. So let's give you an example. I'm going to give you an example. See, 1, 2, Okay. So what's another compound? Let's look at look at let's look at boron. How does boron look like? One electron there. Everyone follow me so far?
Kinda. So you filled in 2 s orbitals and 1 p orbital because that's its electron configuration.
Yeah. I want to figure out for B2, how does I put 2 borons together, how is it going to look like using both these models? So I'm just going to fill in the electrons. Up, down, okay, no big deal. They're identical over here. How about this situation over here? Is there a difference? Is boron paramagnetic or diamagnetic? In real life, we have an experiment to tell us. And boron is paramagnetic. So based on the experiment, boron is paramagnetic is going to have the model on the model A or model B. Which one's the right one, A or B? When we do the experiment, we just get boron 2, put it through our little magnet. Oh, it's magnetic. So we know it's not this one. In this situation, in this model, all the electrons are paired up. So this one's not a magnet. But here, electrons are unpaired. So it is a magnet. So that's how we determine which model to use, because experimentally, it cannot be this one. And the way to explain why boron is magnetic is that the pi electrons here are lower in energy than the sigma electrons. And then the electrons get filled up this way. And this one shows that this boron is paramagnetic, which aligns with our experimental results. So I know there's 2 models here in which someone said, oh, this one's reversed. And that's how we know if it's reversed or not. We could do an experiment, check if the compound is magnetic or not magnetic. Based on that, we know if it's this order or the reverse order. And the only way to do that, you have to do an experiment. You can't just think about it on top of your head and know it. No. You do an experiment, and then the experiment tells us it's B2 is magnetic, and the only way it can be magnetic if it follows this model, and not it's on the one on the right. We will predict it's diamagnetic, and this one is wrong. So how do we know the order? We have to do an experiment. And then right here, they say when you talk about the compounds on the bottom, B2, C2, N2, they follow this pattern. O2, F2, N2 follow the pattern on the right. Oops. So now, this is called the lowest unoccupied molecular orbital. This one's called the highest occupied molecular orbital. So if I put some heat into this molecule, which electrons are going to be moving around? The ones here or this one up here? Which electrons going to be moving around? The low energy electrons or the high energy electrons? High energy, right? So where's the high energy? It's in a certain place. And so this electron, we call that the highest occupied molecular orbital. Your book has the name for that. Where's that electron going to go if I heat it, if I excite this electron? Is the electron going to go down? No, there's nowhere to go. It can't go down. Where's it going to go? It's going to go where? To the lowest unoccupied molecular orbital. Where's the lowest unoccupied? Right here. So the electron could go there. So a lot of chemistry happens in this zone here, from the highest occupied to the lowest unoccupied. So electron could go there, electron could come back down there. A lot of chemistry happens in this little region. So that has a special name. Highest occupied molecular orbital, lowest unoccupied. There's other orbitals on top that are also unoccupied, but that electron is harder to get up there. It takes more energy. So the closest one is called the lowest unoccupied molecular orbital. So I'm looking at this question here. For these problems, we are only looking at the valence configuration. Yes, you could look at the core electrons, but they don't do anything. So we're looking at the valence electrons. Because where did the chemistry happen? In the core electrons or the valence electrons? And when we're at the molecule, which region is chemistry happening? From the highest occupied to the lowest unoccupied. The electrons are going to be going like that. Right? All right. Any other questions? Everyone in shock? Shock and awe?
Yes.
Yes. Probably too stunned to ask a question.
Overwhelmed is a good word.
Well, good.
I think once we work some of the problems, we'll have questions.
So that's why it's so important to read before coming to lecture. Then you have a little idea.
Yeah, I read, I just didn't do the problem. Sometimes reading it's not the same as doing your problems. You have to see where you mess up, and then you see what you don't understand.
All right, perfect. So your homework's going to give you a lot of examples. Then, so once we understand this part, this slide, now we have to tweak it a little bit. So this is a compound called HF. And what happens is, okay, we got HF. How could HF, we know what the structure of HF is. HF is just H and F. We know in real life, we know that that's the compound. So how is the MO theory going to predict that? So what does H have? 1s, right? Electron in the 1s orbital. What does the F have? It has a 1s orbital way down here, but it has a 2p orbital here. And what happens is this 1s from fluorine is so low in energy, it's like way down here. This is so low in energy, it's not near the same energy as this 1s hydrogen, so they can't interact, they're too far away. But 2p for fluorine is very, very electronegative, so the 2p orbital has a low energy, very similar to the 1s, the energy of the 1s orbital. So these two energies are kind of close together. So what's going to interact together? The 1s of the hydrogen and the 2p from the fluorine. So when that happens, we're going to form a sigma bond and a sigma antibond. Right? So where are these electrons going to go? So forget about let's not put this middle part here. So let's just look at this. Where the electron's going to go? Oh, if I do that, something doesn't make sense. I got 1, 2, 3, 4, 5, 6 electrons. How could 6 electrons occupy this? I only have a bonding and antibonding. So what she's saying here is this 2p orbital, not all 3 orbitals are going to interact with this 1s. Only one of these orbitals is going to interact with this one. That's going to lead to that. That. So one electron is going to go down here from this one. One electron from this one is going to go over here. and then nothing over here, 0. How's that problem? Where are these other 4 electrons going to happen? These other 4 electrons, they don't have anyone else to interact with. This 1s orbital is going to interact with this 2p orbital, but these other ones, they don't have anywhere else, nobody else to interact with. There's no other orbital. So if they have no other orbital to interact with, they're just going to stay by themselves as a 2p orbital. Since they have no one else to interact with, we call that non-bonding orbital. They're not involved in bonding. They have nobody else to interact with. So there's some situations which you could have a non-bonding orbital when these electrons have no one to interact with, so they're just going to stay by themselves over here. Only this one will interact. So what's the bond order here? Bond order is going to be 2 minus 0 divided by 2 equals to 1. So this is how we tweak this model to align with HF. Again, no model is perfect. This is just a theory. So sometimes we have to tweak it a little bit, and this is how we tweak it for a compound like HF. Some of these are not going to be involved in bonding. So they're just going to be non-bonding orbitals. Only this one and this one are going to form a bonding and a anti-bonding. So that one puts a little headache into your studying. So now we could interact atomic orbitals, like this is one atom here, one atom here. These atoms come together to form a new molecule, right? But later on, what we could do is instead of putting an atom here, I could put a molecule here. I could put like, I don't know, H2O here, NH3 there. Then I could do the same thing. When these things come together, what am I going to make? So that's what it means here, polyatomic molecules. But we're not going to get into that in this class. But in essence, what we could do is now instead of just having atoms come together, now we got molecules come together and then figure out what the new molecule is going to be. But we're not going to do that for this class. You can do that when you do organic chemistry next year. So that is essentially what this chapter is about, advanced theories in bonding. And just to recap, we did a lot today. Talked about valence bond theory, electrons coming together to form a bond. It's predicted for SH2. When we get to CH4, it doesn't predict. It predicts CH2, not CH4. So what we have to do, we have to do something called hybridization. Make one electron jump from here to over here. Oops. Make one electron jump from here to over there. Now we got 4 unpaired electrons. Now we could have 4 bonds. And those orbitals are going to hybridize, forming something called sp3 hybridize. And we talked about the geometries of this sp3 tetrahedral. Okay. So these we could have hybridization. And S and 2p orbitals could come together. That would give us trigonoplanar. And we talked about sigma bonds, pi bonds. Bond rotation. Sigma bonds rotate, but pi bonds, no rotation. And then we could have sp hybridize, 1s and 1p, 1s and 1p orbital hybridization together to give us a linear compound. And s, p, and d orbitals could come together to give us trigonal bipyramidal. S, P, and then 2Ds could come together to give us a octahedral geometry. And this table is a good table to work on. It tells us about the geometry and the hybridization. And these theories didn't predict that oxygen was paramagnetic. So there's another theory called molecular orbital theory. And this is pretty much the leading theory, or the most current theory of bonding. And it's based on electrons could have constructive, destructive interference. And we call that bonding orbitals, bonding molecular orbitals, or anti-bonding orbitals. Bonding orbital is going to have lower energy than anti-bonding because bonding orbitals are more stable. We can figure out the bond order. So you can put in these compounds. And p orbitals could come together to form pi bonds or sigma bonds. So when p orbitals come together, they're going to form these type of molecular orbitals. And sigma bonds, s bonds, s orbitals come together. It's pretty simple. One bonding, one anti-bonding. That's a pretty simple pattern. One bonding, one anti-bonding. P orbitals is a little bit complicated because you have 3 p orbitals. One of them, they're going to come together, form a sigma bond, and then 2 pi bonds, and a corresponding anti-bonding orbitals. And we do the same thing for oxygen, filling the electrons. This is oxygen here, oxygen over here, filling the electrons. We get predicts that the bond order is 2, and the compound is paramagnetic, which what we see in real life. So this molecular orbit theory is it's a better predictor than Lewis structure or valence bond theory. It's pretty much, and then there's again, highest occupied molecular orbital, lowest unoccupied molecular orbital. And this is where a lot of chemistry happens because that's when the electrons are going to be moving in a molecule from here to here. And when electrons move, chemistry happens. And here we got something called non-bonding orbitals. And that in a nutshell is chapter 8, Advanced Theories of Bonding. And